Imagine pushing a sharp needle into a block of soft gel. Now, imagine taking a blunt spoon and pushing it into that same material. You can apply the exact same amount of mechanical force in both scenarios, but the results are entirely different. The needle drives right through, while the spoon bounces off. It shows us that measuring raw force alone isn't enough to predict a physical outcome. Curious tone. This physical loophole is exploited all the time, often in high-stakes environments like the circus ring. A circus strongman can survive a heavy weight stepping on their chest by first laying down a large, strong wooden plank. The plank doesn't reduce the weight of the object, but it changes how that weight interacts with the body. The total force pressing down is identical, but the plank spreads it across a much wider surface. This concentration of force, the impact felt at any specific point, is what we call pressure. We define average pressure mathematically as the normal force divided by the area it's acting on. Because area is in the denominator, the two values have an inverse relationship. If you keep the force constant but cut the contact area in half, the resulting pressure doubles. The standard unit for this measurement is the Pascal. 1 Pascal is defined as 1 Newton of force applied to a surface of 1 square meter. To understand how objects interact, we have to look past how hard something is pushing and analyze the precise geometry of that push. This logic is easy to see with solid objects, but liquids and gases have no fixed shape. So how can a fluid at rest exert a structured, measurable force? The answer lies in the direction of the impact. In a fluid at rest, the force exerted on any submerged surface is always exactly perpendicular to that surface at every point. We know this must be true because of the laws of equilibrium. If the fluid exerted a force parallel to the surface, there would be a reaction force pushing back that would cause the fluid to flow. Since the fluid is demonstrably at rest, parallel forces cannot exist. The force must be purely perpendicular. This means that for a static fluid, force isn't something that just happens in one direction. It is a structural phenomenon that adjusts to the shape of whatever it touches. How do we measure this perpendicular pressure at a single microscopic point deep inside the fluid? We can use an idealized measuring device, an evacuated chamber with a piston held in place by a calibrated spring. The fluid's perpendicular force pushes the piston inward, compressing the spring until the outward spring force perfectly balances the pressure. Now, imagine shrinking that piston's area until it reaches a single infinitesimal point. Mathematically, the pressure is the limit of the force divided by the area as that area approaches zero. At this microscopic scale, we find that the fluid's pressure remains the same regardless of which way the piston is tilted. Whether the surface is horizontal, vertical, or at an angle, the force per unit area is identical. Because this pressure at a point acts equally in all directions, it has no single directional vector. This is why we define pressure not as a vector, but as a scalar quantity. To apply these rules to the real world, we need one more variable. Unlike solids, we can't always measure the area of a free-flowing liquid. We need a property inherent to the substance itself. That property is mass density, ρ. It's the mass of a fluid divided by its volume. Most liquids are incompressible. Pressure barely changes their volume. Gases are opposite, highly compressible. Their density spikes as pressure crushes the molecules into a smaller space. Density is the missing link. It dictates how much mass is packed into the container, which ultimately determines how that fluid translates force into pressure. When we pull back to the macroscopic world, these microscopic rules govern some of the most extreme environments on Earth. In the deep ocean, the weight of the water column above creates immense environmental pressure that increases with every meter of depth. At a depth of 1 kilometer, the pressure increases by 100 atmospheres. Submarine hulls are engineered to survive this by treating the ocean not as a single downward weight, but as a scalar force that attacks the hull with perfect perpendicular precision at every single point. Whether a needle piercing skin or the ocean crushing a submarine, the physics are the same. Pressure is the story of force meeting geometry.